I'm Eitan Eliyahu. I work for VMware, and we would like to present Open vSwitch for Hyper-V. So basically, we have three parts for this presentation. The first part will be more like architecture level, and the other one will be a little bit in a lower level, and we have like a simple demo at the end of the presentation. So let's start. So Hyper-V, this project was a shared effort for VMware and Cloudbase, and last month we've reached a phase that we actually can demonstrate basic connectivity, and I guess last week or 2 weeks before we demonstrate like operability was OpenStack. So this is an initial phase of implementation. Okay, so we started with some design objectives. So basically, Open vSwitch already was there, and it basically was implemented for Unix-like hypervisors. And we had the challenge to meet Unix-like software with Windows. So apparently, user mode code was really straightforward to implement. So we used almost the whole user mode code with some tweaking for operating system specific services. The kernel mode was rewritten from scratch because of the difference in nature of the operating system and the network stack. We wanted also to be a good citizen in the Hyper-V hypervisor, so we actually followed the Microsoft Virtual Switch, extendable Virtual Switch framework. And we wanted to leverage as much as we can from the operating system, so we leveraged some features like finding route to remote VTAP, and the network stack to do reassembling of UDP packets for tunnels. And another design objective was performance, and one design, this design we are really proud of it. It's like zero copy, which was very challenging in this environment. Okay, so this is the software architecture, which is, we have the right side there, the Virtual Switch extensible, the Hyper-V software, and in the left side is more the OVS plugin. So we need to understand that in Hyper-V we don't write Virtual Switch. We have a Virtual Switch extension, which is actually a filter driver, which overwrites basic forwarding rules, which is used by the built-in Virtual Switch. So basically, one way to see this project is we have two interfaces. One interface is to OVS. When I said OVS, I mean user mode OVS. We need to provide this interface from beneath, and the other side is to be compatible with the Hyper-V Virtual Switch extension. So I will go on this, I will explain in a really high overview of the Hyper-V framework. So this is the model of Hyper-V extendable switch framework. So actually, a vendor writes one of the three extensions. So obviously, we wrote the forwarding extension. And the big block is the virtual switch itself, and the forwarding extension is a filter driver inside the stack. As you can see, we have multiple ports for each guest or child partition. We have the internal network adapter, which is the root partition port, and the stack that we take advantage of it. And we have an external network adapter, which is representation of a physical NIC or multiple physical NICs. Here we'll go through a typical flow, packet flow in the switch. In the network stack, everything is event-driven, and the nature of the driver is asynchronous, and it's certainly as a filter driver. So basically, a virtual machine originates a packet, and then it comes on the ingress part of the virtual switch. The virtual switch calls the extension. So the extension can kind of vetoes the standard rules of the switch, and can overwrite the destination ports in what is called out-of-band structure of the packet. So the packet will come down to the extension, and then the extension will overwrite the destination array port. It will go to the extendable switch, and the extendable switch will distribute the packet to the destination ports. One thing to know is that actually, where you see number 5, the transaction is not done yet. Actually, a control message goes back from the destination virtual machine to number 2 to number 1, and then actually the packet is being completed. This all sequence of event is done through the network stack. So where is OVS? So OVS is in the extension. So we don't do anything on the egress part. We do everything on the ingress part. We install a callback function, which the switch calls us every time there is a packet, or actually a link list of packet. It is called NBL, which is kind of equivalent to SKB. And the packet traverses the extension. We build a flow key out of the packet, and this flow key is being matched to a cache table of flows. Then we take an action according to the flow itself. If there is no match, the packet will be indicated through an opcall to user mode. User mode will take decision what to do with it. Usually, it will return it back to the kernel through the interface, which is, I'll talk after that on the interface itself, but actually we get the raw data and we originate a packet from the extension itself. If the destination is for a remote hypervisor, we kind of reroute the packet to an external virtual tunnel port, which does the encapsulation and send it out through an external port. Okay, so here I'm done with the Hyper-V side, and Nathan will continue with the OVS part.
Okay, thanks, Ethan. So my name is Nitin Raju. I work on the OVS for Hyper-V team. So I'm the filter driver between Ankur, who is at the mini port edge, sorry, at the protocol edge, and Ethan, who is at the mini port edge. So just to emphasize the driver we have. So so we have split this talk into 3 portions, and correspondingly there are 3 takeaways. The first portion is what Ethan covered, which is basically the necessary background into Hyper-V. I mean, many of you folks may not be familiar with Windows. So the necessary background into Hyper-V and how we make use of the switch extensions framework to implement OVS. I mean, I've got questions whether we implemented a switch in entirety. Not really. Basically, we made use of the switch extensions to implement the OVS functionality, which is more than sufficient. So yeah, like you can see, the left side gray box is what OVS is. Obviously, as you can expect, there are two portions to it. One is the user space portion, the other is the kernel portion. In the kernel portion, we have a couple of drivers. The filter driver that Ethan talked about, and also we have something called as a WFP callout driver, which provides auxiliary functionality for receiving and processing encapsulated packets which are fragmented. If it's not fragmented, goes through a filter driver directly. If it's fragmented, it goes through a WFP. But anyway, and in terms of user to kernel interface, we have something called as an open vSwitch device, which is pretty much like a character device that you would find on Linux, where you can register for custom read, write, and control functions. Right? So we've made use of that to interface from kernel to user space. Right? So next I'll go over the different components. Mostly I'll just touch upon the different components we have in both user space and kernel. So this slide is just about kind of the look and feel of the driver. So the name of the driver is called OVS-ext, which we compile using Visual Studio 2013, and we support both WDK 8.0 as well as 8.1. And most of the stuff that we're giving in this talk is also documented in the OVS code repo in datapath windows/design, and it follows the same format of providing some background and then talks about OVS. So now let's start describing the various components in the kernel. So the first thing I want to talk about is how we interface with the NDIS stack. Ethan has kind of given us some background, so that helps a lot here. So what happens is when the driver loads, when the module loads, we kind of register with the NDIS framework to say that we are a filter driver, or we provide filter driver functionality, right? So that said, things are not done. I mean, the driver is not really activated or anything of that sort. So since OVS kind of makes use of the extension functionality, OVS extension needs to be enabled on a Hyper-V switch, right? So we kind of wait for this enablement, which is also called attach handler in NDIS terms. So when OVS is enabled on a Hyper-V switch, we basically create the OVS data path, right? So that is basically what I mean to say that until OVS is enabled on a Hyper-V switch, running OVS dpktl show will not show any output. The other thing is that we support a single data path for now. That implies that we support enabling OVS on only one of the Hyper-V switches, and which is more than sufficient for the purposes of OVS, because user space also makes use of a single data path. Right? So, and once the OVS extension is enabled and data path is created, there are two modes of interfacing with NDIS. Like you can expect a control path and the data path. Control path is mainly for things like new port getting created or a port getting updated and things like that. And data path is mostly for packets. So this slide is about how we interface with user space. Like already mentioned, we use a pseudo device to interface with user space, and user space kind of takes advantage of this, and we emulates netlink sockets based on the handles that we create to the pseudo device, right? So there is user space code in netlink socket.c, which emulates all of the NL star APIs, the netlink socket create or the dump start or the transact and all that. Then in terms of messages that are exchanged between user space and kernel, these are basically netlink messages, right? So and the families and the commands that we support are the same things that are supported on on Linux, which is in openvswitch.h. That said, we had to write a few custom commands specifically for Windows, which are documented in OVSDP interface ext.h. I mean, this file also follows the same format as openvswitch.h, where the file acts both as a header file as well as documentation. Right? We'll go over what extensions there are, but it suffices to say that just the openvswitch commands were not sufficient, and we needed to implement some extensions. So in this slide, we'll talk about port management. One of the key things is that we added a field in each Hyper-V port. I mean, not added, but for simplicity, let's say added. So we added a new field in each Hyper-V port and called it the OVS port name, right? And what this field represents is basically the same as the name field in the interface table on OVSDB, right? So whatever value is set for name, you set it in the OVS port name in Hyper-V port. And why do we do that? We do that because when this port shows up on Hyper-V switch, we need a way to map the Hyper-V port to the port added from vSwitch-T. So that's why we added a new field. And like Ethan mentioned earlier, we have something called an internal port on each Hyper-V switch. And internal port is nothing but a virtual adapter that shows up on the host. And this virtual adapter, you can assign IP addresses and things like that, right? So we repurpose that for VTEP functionality and use that for ARP resolution and IP route lookup and all that. And in addition, for ports themselves, we support create port and delete port and update port kind of notifications. So like Ethan mentioned earlier, one of the key innovations we did was we implemented a kind of a sophisticated buffer management system. So the purpose of implementing that was to achieve zero copy within the OVS extension itself, right? Obviously, we don't have any control outside of the extension, but within the extension, let's say, for example, when a VM sends a packet, and OVS being just a filter driver doesn't really have the authority to modify the packet. So what we do is we need to make copies, and when we make a copy, we implemented functionality to just deep copy the portions of the packet that we need to modify and shallow copy the rest. Yes, NDIS does not provide APIs that were directly usable for this. So we wrote APIs using a bunch of NDIS APIs. And one key difference between OVS Hyper-V and OVS for Linux or other platforms is that in terms of how we handle encapsulated packets. So we don't really punt encapsulated packets over to the host IP stack. So what we do is we have a module called as the IP helper, which queries the host for ARP lookups and route lookups and caches them, and we kind of inline forward an encapsulated packet to the physical interface. So that's one of the differences. It need not be that way forever, but that's how it's been written for now, right? So in terms of tunneling protocols, we support VXLAN for now. VXLAN encapsulation, but it's very easy to extend it to other ones. So sometimes we need to implement some offloads that have been requested by WIFs. For example, when we need to do encapsulation, we need to complete the offloads before we encapsulate a packet, right? So we support TSO as well as in the TSO and checksum in the transmit direction, and in the receive direction we support checksum verification. And because I guess the packets need to be, some of the packets when they missed or if there's a user space action, we need to send to user space. We support a packet notification in the kernel so that user space doesn't need to do busy polling. So that kind of completes all the components that I kind of wanted to touch upon in the kernel. Let's move on to user space components now. User space, like Ethan mentioned earlier, obviously it was a huge effort to port POSIX or Linux code to Windows, right? So that happened separately, and that had nothing to do with interfacing with the kernel directly. So most recently, we worked on porting the portion of user space code that interfaces with the kernel data path, meaning the netlink and the DPIF provider code. And like I mentioned earlier about netlink, basically we emulated netlink sockets and all of the netlink APIs that were required. For example, things like get PID. There is no PID as such, so we kind of generate a PID for each handle in the kernel, send it up, and we return that to the higher level layers in OVS. Right, so in terms of DPIF provider, what was DPIF Linux earlier became DPIF Netlink now, because it's not really specific to Linux as such. Right, so we have kind of reused the DPIF provider code. And Windows doesn't really provide or support NetDev API as such. So we basically had to implement these APIs in terms of netlink extensions in the kernel data path and expose them as part of the header file that I mentioned earlier. So this slide is one of the most important things we did. Like I mentioned earlier, in each Hyper-V port, we added a field for OVS port name, right? And what is this OVS port name field? It's the same as the name field in the interface table in OVSDB, right? So, and we had to provide a command line utility to specifically, this is specific to Windows, where you can set the name of the value of the OVS port name in each port, right? So I've just provided an example here. So for a name, for a VM which is called Ubuntu-VM, to set the OVS port name, it supports port name being VIF port 1, we can use this command. I mean, this assumes that there's one VIF and all that, but obviously we have other commands for multiple VIFs. So that kind of mostly concludes my portion of the talk. So again, the takeaway was how was OVS implemented using the Windows extensions. So for the third part, I call my colleague Ankur Sharma to kind of cover the fun stuff. Thank you.
You're on. Yeah, you're on.
So third takeaway from this presentation is to basically show you how to get OVS up and running on Hyper-V. We will be showing it through a simple demo where we have two Hyper-V servers which are connected to each other through a VXLAN tunnel. We'll be showing a demo video now. Just a second. So very first step in the installation is to basically install the driver. Installing the driver is as easy as just running that install.cmd script. Once the driver is installed, then any Hyper-V switch is going to show OVS as a forwarding extension. For example, we have a Hyper-V switch here. If we go to extensions, now we can see that it shows that, okay, we can enable an OVS extension now. So we enable it here. So at this stage, the kernel side of things are done. Basically, installing the driver is done. We'll move to basic OVS steps now. First one is starting the OVSDB server. We start vSwitch-D. Now comes a Hyper-V specific part. So as Nitin mentioned, we have implemented a new command which is used to provide a name to a VM's VNIC. So we have this virtual machine and it has a VNIC running. So first thing that we are going to do is we are going to execute our Hyper-V specific commandlet to give a name to this VNIC. So this is the script ovs.psm which has the commandlet implemented. So we basically give the name of the VM. We mention that it has a VNIC, and then we say that, okay, that for this VNIC, set up a name. So for example, here we are saying that name should be WinPort2. So now we connect the VNIC to our Hyper-V switch. Last but not the least, the same port has to be added to OVSDB as well. So we execute OVS vsctl add port. Please note that the name of the port here will be same as what we gave when we executed the Hyper-V specific commandlet, which is WinPort2. So at this stage, our OVSDB and our kernel data path is all set. Let's execute vsctl and check the DB state. So we can see that WinPort2 has been added to OVSDB. We execute dpctl to check the kernel state. And we can see that same port is on the kernel side as well. So at this stage, we are done with the setup. The port is there in both kernel and in user space. So we can basically start running traffic. So as mentioned, we have second hypervisor as well, which has all the setting done, and it has a VM running, which is 10.0.0.1. So from this hypervisor's VM, which is 10.0.0.2, we basically try to ping 10.0.0.1. And that kind of finishes the demo. The traffic part, the traffic is working. A few things to note here is that in the demo, we have shown that both the machines were Hyper-Vs, but it can work with any platform which supports OVS, for example, KVM. Our implementation works with a controller as well. Recently in OpenStack Summit, we have shown a demo in which it worked with NSX controller. And with the help of Cloudbase, we have been able to get the Hyper-V integrated with OpenStack as well. Yeah, so that finishes the presentation from our side, and we are ready for questions.
Hi, Luigi Vizzo, Università di Pisa. Very interesting presentation. I see you were concerned about performance doing the zero copy in the kernel. So can you tell us a bit more on the native performance of the Hyper-V switch before your extension?
Unfortunately, we've not measured performance yet. I mean, we just got this whole thing to work a couple of weeks ago. But in terms of, so are you asking native performance of the Hyper-V switch itself or with us enabled? Both. Okay. So with the Hyper-V switch itself, I don't know, I'm only speculating at this point, but if the use of any hardware offloads, then they can get good performance. And if we insert ourselves in between, and we do something like VXLAN tunneling, then we'll not be able to leverage hardware offloads, right? So performance may not be as good. So that said, we haven't measured anything yet.
Okay, thanks.
So one of the great features of the OVS, Bob Lance Open Networking Lab, and I also work on Mininet. One of the great things about the Linux OVS is you can instantiate multiple OVS instances. Even though they share the same kernel module. One thing that wasn't clear from your presentation is whether you can do this on the Windows version, and if you can't, how difficult would it be to allow you to have multiple virtual switches?
Thank you.
Can I start by, this is Ben Pfaff from VMware. Do you mean, Bob, that you can add multiple bridges to a OVS switch, or do you mean multiple data paths in the kernel? Maybe you should clarify your question.
Doesn't matter either way. Just from the just to allow you to specify multiple switches that could, for example, have multiple flow tables and sort of allow you to create a virtual network consisting of multiple OpenFlow switches, for example, on your Windows machine, the same way you can do on Linux. And so it's a little bit, I guess, to answer Ben's question, it's not the same as just having multiple VLANs on a single bridge. Rather, multiple Open vSwitch instances connected together in some topology that you could specify.
Okay, thank you. So, like what Ben was saying, there is a key difference whether you're asking for multiple bridges in OVS itself or multiple data paths in the kernel, right? So, right. So, multiple bridges in OVS we do support, right? I mean, most of the functionality is in OVS user space, and you can pretty much create a BR-int1, BR-int2, whatever you want. So that is supported. But in terms of kernel data path itself, we support one data path. And that is mostly what OVS in its current form needs. So there's only one OVS test system, which is the data path, and we support that, and that's more than sufficient.
Do we have any other questions?
This is Roxana from One Convergence. So I have two questions. The first one, what were the triggers for this port? Was it just for VXLAN support? And the second question is, you mentioned that VXLAN offloads are not supported as yet, but in one of your slides you mentioned that you do have TSO completion and CSO taken care of. So I was wondering whether you can clarify that.
Sure. So in terms of why we did this, I guess VMware is interested in supporting Hyper-V also in their controller. So that was one motivation, and why we did with OpenVSwitch, so that I guess Open vSwitch has been proven, so we use that. Right? That's one that answers your first question. So regarding your second question about offloads, so what I meant to say was that so there is NDIS or Windows doesn't really expose two filter drivers. I guess a framework to take advantage of a VXLAN of a NIC which supports VXLAN offload in hardware, right? So if we did that, then like a 64K buffer that comes from a VM we could just set some VXLAN context, send it down to the physical NIC if end is supported, and the NIC would take care of splitting it up into smaller packets. So we don't have that support. So without that, OVS will have to sort of complete the offload request, right? So that's where the TSO context came in. So we have to complete TSO before we do the encapsulation. Yes, but we don't support NVGRE yet. And even when we support GRE, I don't think Hyper-V really exposes a framework such that filter drivers can take advantage of it. Right? I mean, the NVGRE functionality that's implemented is within the Hyper-V network virtualization stack. That is separate from the NDIS filter drivers. Okay.
My name is Songbo Wang. I just want to ask you about how the vSwitch D you can compile in the GCC compiling or use the Visual C++.
We used Visual C++, Visual Studio 2013.
So I just using your manual about using the AUX the compiler, but it doesn't work.
WF no.
So I just wonder, how about your environment, your building environment in the...
Okay. Yeah, good question. So, like back in, I think last November, so like Ethan mentioned, we worked with this other company called Cloudbase, right? So they wanted to get this going, that's compiling user space with Visual Studio. So, but we wanted to make it consistent with other platforms. Yeah. So basically we use AutoConf and Make to compile user space. That said, that's not completely integrated with how we compile the kernel, right? So you can run a top-level Make today, and that would go and kick off the Visual Studio Make file and compile the kernel extension. But so if you go so there's a file called install.windows. If you go there, that basically lists the packages you need to install. One of them are basically Visual Studio before you can run Make. So you run boot.sh or configure all those things, but a prerequisite is that you need to have something called as MinGW, which provides emulation for Unix environment. Then we need pthreads. Then we need Visual Studio. All these things are prerequisites before we can compile it the way you do it on Linux.
Do we have any more questions? All right, let's thank our speakers.
Thanks so much.